What's up, guys? Welcome back to a new one. Today, we're going to be looking at Doubly link lists. It's a different type of link list here. But before I do get into it, if you're not subscribed, click on that subscribe button and then also check out the first link in the description. It's a free guide I have, the coding directory, which will teach you how to get an internship or a job in tech completely for free. So check that out. Once you do sign up, I believe it does take a second or two to come into your inbox, and then you should be good to go from there. But let's get into the doubly linked list here. So, like a singly linked list, a doubly linked list is comprised of a series of nodes. Each node contains data and two links or pointers to the next and the previous nodes in the list. The head node is the node at the beginning of the list, and the tail node is the node at the end of the list. The head node's previous pointer is set to null, and the tail node's next pointer is set to null. So again, if we have A here, node A, this would be null, the previous node, because there's nothing here, and this node, there's nothing here. So think of a daily commute on the subway as a real-world example of a doubly linked list. Your home is the head of the list, your place of work is the tail, and every stop in between is another node in the list. In the morning, when you take the subway to get to work, you're traversing the list from head to tail using the stop's next pointer. While this can be done using a singly linked list, a doubly linked list will also traverse back to where you started using the stop's previous pointer. So you will take the exact same route to get home, just in reverse. So common operations on a doubly linked list may include adding nodes to both ends of the list, removing nodes from both ends of the list, finding and removing a node from anywhere in the list, and then traversing through the list. And then adding to a list. So in a doubly linked list, adding to the list is a little complicated, as we have to keep track of and set the node's previous pointer as well as update the tail of the list if necessary. So adding to the head. So when adding to the head of the doubly linked list, we first need to check if there is a current head to the list. If there isn't, then the list is empty and we can simply make our new head both the head and the tail of the list and set pointers to null. If the list is not empty, then we will set the current head's previous pointer to our new head, and then set the new head's next pointer to the current head, and then set the new head's previous pointer to null. So basically, when we're adding to the head, what happens is, let's say we are doing this, okay? So we have this node A and node B, and we want to add node C. So first, we have to make the previous node null. First, we have to do the current head node. We have to point it at this one as the previous node, and then we make this previous node null, and then we make this next node as this one, and then we set this next node as node B. So that's really how it works. And then adding to the tail is similarly, there are two cases when adding to a node to the tail of a doubly linked list as well. If the list is empty, then we can just make the new node to the head and tail of the list and set the pointers to null. If the list is not empty, so if it's just like one thing, you can just insert it and be like, okay, the previous one is null, the next one is null. But if it's not empty, if you have, let's say, two or more, then you have to set the current tail next pointer to the new tail, and then you have to set the new tail's previous pointer to the current tail. So this new node is going to be null, okay? And then set the new tail's previous pointer to the current tail, and then set the new tail's next pointer to null. Okay. and then removing from the head and tail. So due to the extra pointer and tail property, removing the head from a doubly linked list is slightly more complicated than removing it from a singly linked list. However, the previous pointer and tail property make it much simpler to remove the tail of the list, as we don't need to traverse the entire list to be able to do it. So removing the head just involves updating the pointer at the beginning of the list. We'll set the previous pointer of the new head, which is the element directly after the current head, to null, and update the head property of the list. If the head was also the tail removal process will occur as well. Similarly, removing the tail involves updating the pointer at the end of the list. We will set the next pointer of the new tail to null, because you're removing this one, so you have to set it to null now. And then update the tail property of the list. And then if the tail was also the head removal process will also occur. So it'll just get, both sides will just become null. But yeah, to remove the head, you set the previous node to be null, and that's really it. And then you just get rid of this one. And then for this one, removing the tail, you set the next node to be null, get rid of it, and that's the tail. It's pretty straightforward of removing it. Removing from the middle of the list, so it is also possible to remove a node from the middle of the list, since that node is neither the tail nor the head of the list. There are 2 pointers that must be updated. We must set the removed node's preceding node's next pointer to its following node. And then we must set the removed node's following node's previous pointer to its preceding. So basically what it means is if you're trying to remove this one, you have to set the previous node stays null, of course, but this one gets updated to this node because this has to point to this one, and then this one has to point to that one as the next. So it's the same thing as a singly linked list. It's just you have to keep track of both sides, the present and the future. So there's no need to change the pointers of the removed node, as updating the pointers of its neighborhood nodes will remove it from the list. If no nodes in the list are pointing to it, the node is orphaned and therefore it gets shattered and you're left with this one. So it starts off with 3, you do the appropriate pointing, and then this one just vanishes because it doesn't have anything to combine it. And then let's take a minute to review what we've covered about the doubly linked lists in this video. So doubly linked lists are comprised of nodes that contain links to the next and the previous nodes, are bidirectional, meaning it can be traversed in both directions, have a pointer to a single head node, which serves as the first node in the list, and then they have a pointer to a single tail node, which serves as the last node in the list. They require the pointers at the head of the list to be updated after addition to or removal of the head, and then requires the pointers at the tail of the list to be updated after the addition or the removal of the tail. And then also require the pointers of surrounding nodes to be updated after the removal from like middle of the list as well. So you can have a longer doubly linked list. Let's say you had a node D here. If you want to get rid of node C, the same thing would apply, of course. And then we have a little quiz here, so we'll take it right now. So doubly linked lists are bidirectional. True. Consider A, B, C, and D. When removing node B, the pointers of which nodes should be updated? Node A and node C should, because yeah. Doubly linked lists contain all of the following except children, data, next pointer, children, because it contains data and it contains a next pointer and a previous pointer. It doesn't have any children. Doubly linked lists have all of the following except a tail, a direction, nodes with 2 pointers, a head. I believe it's a direction. Yeah, because they're bi-directional, so they don't have a specific direction there. And then consider no A to B, and then they're back, B to C, and then they're bidirectional. So when removing node C, the pointers of which nodes should be updated? Just node B should point to null, so just node B. Because if you don't do anything to C, it gets orphaned and it just vanishes, remember, so we don't have to do anything there. Consider the same linked list here. When removing node A, the pointers of which node should be updated. So when we're trying to get rid of A, we just fix up B and no A just disappears. So we got a perfect 100 on there. We're gonna earn some more computer science experience points. And then in the next video, we'll be looking at the doubly linked lists in Python. So stay tuned for that, but this is going to end it right here. Thank you so much for watching. If you enjoyed, consider subscribing if you found any value, and I'll see you in the next one.